the third lecture, or Mikko, on thermal field theory.
Okay, good. So today we'll discuss a little bit similar topics that Misha was discussing. So bubbles, nucleation, dynamics. This is a little bit more qualitative than yesterday, so lots of plots. But hopefully it's helpful, because often this is a topic that one doesn't really learn in regular lectures so much, so sometimes it comes kind of out of nowhere. But before I start drawing plots, we need to do just a couple of lines of basic thermodynamics. It's always a bit difficult. I mean, the equations are very simple, but then one has to think very hard what they mean. But okay, we can start with the second law of thermodynamics. One can write it in many different ways, but one way to say it is that, well, if you have a change in energy, then if it's a certain type of energy, internal thermal energy, then it corresponds to a change in entropy. These are the usual quantities in text, so I will normally use these small letters, and these are then the densities, so everything normalized to the volume. Okay, so now, in particular, in a first-order transition, it so happens that there is such a delta S if you go from one phase to the other. You really need to insert energy to the system to heat it up. So to boil 1 liter of water, you need to insert a certain amount of, you have to use electricity, and a sufficient amount of electricity to have all the water boiled. You need this energy. So we call in cosmology, we normalize then everything to the volume, and what we call then the latent heat is the delta of the energy density. Of the small e. So now, usually what we compute, and what we in particular computed with the effective potential, is not the energy, it's the free energy. And free energy is a Legendre transform of the energy. And free energy has a certain differential, and let me just write that if one writes dF, then its variable temperature, it's natural variable, so it goes like minus S times dt plus 10 other terms. So now what we see from here is that in the free energy, actually there is no discontinuity. Delta F at T critical temperature is delta E minus the critical temperature is, there's no discontinuity in the temperature, it's Tc. But since these two are equal at the critical temperature, then delta F is 0. And so this corresponds just to the plot that we've had, where we plotted things in terms of some maybe phi bar. We had the effective potential, but the effective potential is exactly the free energy density, the small f. And in a first-order transition, we have these two minima, and they are degenerate exactly at the critical temperature. And so then there is no discontinuity in the delta, in the f. Now, the S is minus d dt of delta F. And so therefore, the latent heat Tc delta S is minus dc dt of the small f. And so now the point is that the latent heat exists. So even though delta F is 0 at Tc, then the latent heat is non-zero because delta F is a function of T. That means that if you go below Tc, then there is a delta F. And if you are above Tc, there is a delta F. And if you were to plot delta F as a function of T, then it's true that it's 0 here. But with my normalization, my delta F is the high temperature phase minus the low temperature phase. Therefore, I see that if I'm at above Tc, the high temperature phase has a lower free energy. So delta F is negative. At low temperature, high temperature phase has a higher free energy. Delta F is positive. So it's a curve like this. And so it has a gradient. It has a gradient, and if you take the minus the gradient, that gives the latent heat. And the latent heat means that the energy density is discontinuous. Okay, so what does that mean? So now in a thermal system, and in particular in the early universe, we need to account both for the free energy, that's kind of the variable in our computations, but also of the energy. Energy is also important. Energy appears, for instance, in the Friedmann equations. That really has energy and pressure, not the free energy, but the energy and pressure. And so in particular, it means that if we look at what happens in the early universe as a function of time, and now I plot here the temperature, and then there is Tc here. Then we may start from somewhere, early times, maybe inflation something. So at, let's say, time extremely early, we may not be able to define the concept of a temperature at all, but at some point we have a temperature, it's a high one, and then it goes down. But when the temperature hits Tc, and if it's a first order transition, it cannot just go through. It cannot go through because at Tc, there is the latent heat. So we release energy. And this, in the universe, the energy just cannot go anywhere. There's no other reservoir where I could put the energy. The only way that we can account for this energy is that we stay at Tc and let the expansion redshift away the energy that we get from this transition. So in an ideal system, a first order transition looks like that. You stay for a while at Tc, and then you continue once you have diluted the latent heat. So this is the idealized scenario. So now the real world is even more complicated, and the reason is that we are really expanding in real time. So somehow when one comes here, I mean, the system, it just cannot react instantaneously. It cannot instantaneously decide that, oh, now I have to do something completely different and stay here and start dissipating the energy. Everything takes time. Dissipation of energy takes time. One has to find some process which takes this energy and gives it to some other degrees of freedom, dissipates it. So what actually happens is that we don't go immediately to this kind of a Tc, but we rather, the system supercools. It takes time for it to react. And then there is some complicated dynamics. And depending on the dynamics, it then depends on what happens. Maybe it then reheats to Tc, or maybe this dynamics takes so long that then it at some point hits this curve, and then it continues in a simple way. So that's somehow this complicated dynamics, which we usually think of as bubble dynamics. And we'll come to that. Okay, so the goal today is somehow to try to understand a bit the ingredients here. And so So also at the end of the lecture or towards the end, I mean, this was just arguing that things cannot happen immediately, that it takes a while. But actually we can do a computation. And we'll come back to that. We will show, it's not difficult to show, but we will show that really the likelihood to immediately at TC to go into the other phase, it's just exponentially small. It just doesn't happen. So you really have to go a bit down, super cool, and then the probability to do something becomes finite. It's very nice to see and understand that. Okay, so the general process I mean, probably in the real world, everything happens at once or simultaneously. Many things go on simultaneously, and it's complicated, but somehow to describe this, we like to factorize this in sort of different ingredients. And the first ingredient is then the nucleation of bubbles of the low T phase. So this is now a kind of like a snapshot of the universe at some temperature which is a little bit below Tc, and most of these things, most of the plasma is still in the supercooled high T phase. One often calls this the force vacuum, but it's not really maybe very nice because this is not vacuum. This is a very thermal system. Many states are occupied, but so I try to call it the high T phase. And so that what can happen is that out of thermal fluctuations or quantum fluctuations also will come to that, you can nucleate a bubble. And one can really think of these as well as the type of bubbles one sees when water boils. So one can nucleate a bubble. One could nucleate bubbles of different sizes. If one has a bubble which is just very small, like a small drop, like a thermal fluctuation, very small, then actually it shrinks. It doesn't sustain itself. Small bubbles shrink. And if the bubble is large enough, then it starts to grow. So basically, our first task will be to find out what's the probability of nucleating a bubble which is really large enough such that it starts to grow. That can bring us in the right direction. Okay, that's the first thing. Then the second step is that these bubbles, if it's large enough, it starts to grow. So we like to imagine that there is a stage where these bubbles are kind of growing, stationary growth. Of large bubbles. Now this in itself is very interesting and actually quite non-trivial. And the reason is the following. So let's think of here as I'll just draw first like a bubble. And I put some point in the center and point far away. And this bubble is supposed to be growing. So now one has to think about boundary conditions. And if we are far away from the bubble, then on the average, the medium, this plasma, is at rest. If you go inside the bubble, just in the center, there also the medium has to be at rest because there's no directionality. I mean, all directions are equally viable, so the only choice is that the velocity is 0. You cannot say that matter would be flowing in some direction because it would break symmetry. So at the center of a bubble, I think that's intuitive. Also, medium is at rest. Medium is for me like the plasma.
Mikko, here, I have a question. In this diagram where you go flat, imagine even in the idealized case, you still expand, even though the temperature is constant.
Yes.
So this expansion should be controlled by some fiducial parameter.
Yes, exactly.
What is it? The entropy?
Well, you can, I mean, I think the simplest way to describe is that you reparameterize the energy density as the energy density of, let's say, Tc plus of the high temperature phase, and then some volume fraction of that plus E Tc minus 1 minus S, this volume fraction. So it's sort of, I think that's the simplest, the geometric picture that part of the physics, part of the plasma has gone into the other phase and the rest is. And so you have to, then you don't use in your equations then temperature as a variable, but as long as you are on this curve, you instead change to another variable and describe it like that. And once the variable becomes 0, then you continue with the usual expansion.
Yeah. Thank you.
Want to clarify something to me. In your definition of the energy, you are disconsidering pressure and a variation of volume because you define the variation of energy as TdS. So you are disconsidering other kinds of variation.
I mean, right. So okay, very good. So I'm assuming, in particular, I'm assuming that the chemical potentials are essentially 0. In cosmology, it's a very good assumption. So basically, there are no conserved particle numbers. I mean, there are some, like baryon, very interesting, but like for the thermodynamics, they don't matter for the, it's like mu is 10 to minus, chemical potentials in units of the temperature are sort of the order of 10 to minus 10. So we can, in a very good approximation, set them to 0. So then, moreover, I scale everything with a volume. So, usually you have TdS, PdV, mu dn, but mu is 0, so no mu dn, and I scale everything with a volume, and then one can rewrite the equations scaling everything with a volume, and then also these PdV, the dV terms drop out. So then everything is in the temperature and the entropy, yeah. Good. So what's the problem here? So imagine that you are sitting here, you are at rest, and then there's this phase boundary, it comes, and it hits you, like with almost the speed of light. So you will fall, or something happens to you. I mean, it sets you in motion. It's kind of necessary. If you are hit with this boundary, it just sets everything in motion. And so behind a boundary, things move. There is a velocity to all the particles. But now we have a conflict. So velocity is 0 here. Then things are moving, but then they again must be at rest. So it's very simple argument, but actually has very kind of deep, famous consequence, which is that if you have a phase transition and there's a bubble, there are always two boundaries. There has to be another boundary here, which again sets the medium at rest. That's the only way you can satisfy both conditions. And so now this is a sort of a topic of hydrodynamics in itself, like hydrodynamics of phase transitions. And so basically there are two solutions, two classes of solutions. So I will plot here like v is the flow velocity, more precisely it's the flow velocity in the radial direction here. I call this the radial coordinate, and this is the flow velocity in the radial direction. And then I plot it as a function of r. Actually, I'll take r over time. Maybe I should call this is not the cosmological time, this is the time from the nucleation. So let's say delta t. So now one solution looks like this, that you are first hit by something, and what you are hit by is a shock. Call it a shock. And then behind the shock you are in motion, and then there is another boundary, and that's the phase transition. And the shock moves at a velocity which is larger than or maybe equal to the speed of not light but of sound. That's the speed of how fast signals propagate in matter. It's the speed of sound. So shock is like a sound wave, except that it's an extremely violent sound wave. It's discontinuous. Like in pressure, there is like a discontinuity in ideal hydrodynamics. And then there's a phase transition, and this is a velocity which people normally call the velocity of the wall velocity, VW. And this type of a solution is called a deflagration. And then the other possibility is that so now this is really the phase transition, and this is just a shock without a phase transition, just in the medium. This is like the low T phase, and this is the high T phase. So it's a shock in the high T phase, propagating in the high T phase. There's another solution which is then the opposite. Where maybe I should put the phase transition with some color. And so in the other case, you put the phase transition first. Like this. And then behind it, there is some kind of a profile, which then comes to an end at some point. This is called a rarefaction. These things were studied a lot by famous people like von Neumann and stuff in the 40s. I don't know why, for some reason. Declassified them after the war. And this is called the detonation. And so it's really kind of one can find these solutions, these properties, and now here the velocity, this is then the wall velocity, and this is then larger than or of the order of the speed of sound, and then here are smaller velocities, and so everything is subluminal, of course, but not so much. So the speed of sound in ultra-relativistic matter is 1 over square root of 3, so 0.6. So these are very, very large velocities. Okay, and so now, for instance, when people do baryogenesis, this type of processes that Misha was sketching, or gravitational waves or whatnot, then actually this matters very much in which regime you are. This wall velocity is a very important parameter in all these computations. And so you somehow, if one wants to do a quantitative computation, then one has to go through all of this and try to figure out which of these two it is and what is the wall velocity and so forth.
Can you have a type of solution of both cases? Like
yeah, then there is some special class where you kind of you have in some sense three fronts or so. You kind of combine these a bit. People sometimes call it a hybrid solution or so. But this is a very special case. Yeah.
Okay. Another question. Why can you say that the bubble will reach the stationary regime before the end of the transition?
It's sort of another, I mean, so for me, I was just saying, it's kind of, okay, so it has to do a bit with the time, with the scales. So one could, normally one finds that the bubbles are quite small compared with so very small, initially very small compared with the Hubble radius. And the distances are also much smaller than the Hubble radius, but still much larger than the initial radii. So there's kind of a lot of space, like many orders of magnitude, before the neighboring bubbles start colliding.
Okay.
So there's time for the system to settle in a stationary
Okay, thank you.
motion.
There's another question.
Is there any physical intuition, like to have this behavior, like it's going this or this, and not like go up and down, or not intermediate velocity, but why it grows linearly?
What goes linearly?
The velocity when we've already radius.
So these discontinuities, these are, okay, so this is not exactly linear. It's some solution of the you have to put in the equation. It's some non-trivial profile. It's not exactly linear. You have to work it out from the hydrodynamics.
Okay, so it comes directly from hydrodynamics.
Yes, exactly. You have to solve the hydrodynamic equations. They are nonlinear equations, but one can find, for simple, then if one has a simple equation of state, one can find actually the solution, and it's not exactly linear, but sort of it looks a bit like that if you plot it. Yeah.
Okay, but this comes like directly from the shock wave physics.
Yeah, I mean, you solve the equation here, then hydrodynamics also allows for discontinuities, but you have to satisfy some kind of condition across like in optics, you have matching conditions across the discontinuity. Also, the same in hydrodynamics. You have a solution here. Here you have trivial solutions. Here you have matching conditions. Then you have to put everything together such that you satisfy all the constraints, and then you find these solutions.
Okay, thanks.
Sorry, there are more questions.
If you have a bubble that is not perfectly isotropic, but it has small perturbations, anisotropies will still grow?
Yeah, it still grows. I mean, this was also a question, I think, with Mitch. And so, yeah, one can analyze what happens if you put small perturbations here. Actually, it's a very hard problem in hydrodynamics to analyze the instabilities. So Mitchell was saying that they shrink, that they oscillate or shrink, but don't go exponentially. I think that's at least that's the usual common wisdom. But still, these are very small scale. I mean, these bubbles, they become really macroscopic after a while. And these perturbations, I think that certainly always in statistical systems, there are always perturbations. For sure, there are always, it's not completely spherical. There are small perturbations always, but usually we have an average value and then small perturbations. And as long as the perturbations don't really grow exponentially, then they don't matter so much for the big picture.
One more.
For me, it's not completely clear yet, this concept of bubble. Can you explain a little bit more or give him some kind of analogy, please?
Well, but I mean, I think really this boiling of water is the simplest analogy you can have. You imagine that you are boiling water. There you go in the other direction. You start with water, then you put it heat it up to 100 degrees, and then you just see that there are bubbles forming of the vapor. I mean, bubbles which don't have water, but instead have water vapor. These are the kind of simplest bubbles that of course, it happens in the opposite direction. If you take water vapor and then you cool it down, then it condenses to water droplets, to rain or so. I mean, these are rain droplets are bubbles, if you wish. The physics is a bit different because they don't grow so much unless they find each other. Here, really, somehow they grow very separately. Yeah. Okay. Then there's the third stage, which is the most complicated, which is then bubble. At some point, they start colliding. Now, I mentioned the speed of sound. The shocks is kind of a very hard sound. It hits you. But also these collisions, even if the velocities were a bit less than speed of sound, they can still be like 0.2 or 0.1 of the speed of light. So these are really still ultra-relativistic velocities. So when these bubbles collide, it really creates a lot of noise, so to say. So people talk about sound waves produced by all these collisions. And then it's a very complicated system. At the end, maybe there is some turbulence and so forth. And so this is really extremely complicated physics. That it's complicated doesn't mean that it wouldn't be important. It's considered to be very important. It's considered important for gravitational waves. It's probably also important for baryogenesis, but it's just so complicated that we kind of hope that we don't need to say too much about it, because really the only way to do this well is somehow numerical simulations. Of course, nowadays people are doing this, but at least for the first two stages, we can also do something analytically. So that's what we will try to do today. So I will not go into this phase. Okay, so now I want to start with the first thing and the nucleation, and I first want to kind of describe how we can address, or at least address some aspects of the nucleations in field theory. Let me still first draw a sketch again of, we have our field phi bar, then we have some effective potential, and we imagine now that we have supercooled a little bit, so that the potential looks like this. But initially we are here, we are supercooled, so the temperature is below TC, that would be the preferred state, but we are somehow here. But it's a thermal system, so if one thinks of quantum mechanics, we are kind of occupying many levels here. It's not only ground state, it's many levels that we are occupying here. And so somehow we have to get here. And if your intuition is from quantum mechanics, you would say that, well, it's a wall, but I can always tunnel through it. And if instead you have been thinking about statistical physics, you would say that, well, there's no reason to go through the wall. I can just take a thermal fluctuation, the Boltzmann weight, and I can go above it. Now, of course, in the real world, it's not either or. Somehow these have to be separate limits of common behavior. And that's what I'll try to illustrate you, how it can be that these two completely different sounding phenomena are actually separate limits of a common behavior. So one reason why I want to do this is because there's a nice connection now to what we introduced. Namely, we introduced to do our computations, the effective potential, free energy density, we introduced this object, this Euclidean action, this imaginary time action. Euclidean action. And it sounded like just a mathematical construction living in this funny periodic extra dimension. But actually, this action has also other uses, and in particular, one can understand something about the nucleation with this action. And so now, suppose we take this action. So it's a functional of our fields. I'll again use the notation of just putting some scalar field there to simplify the discussion. So now we can look for solutions of the equations of motion. So we vary the action with respect to the field, and we look for solutions of equations of motion. So this is like a semi-classical expansion. It's not the same as the full path integral, but often it's a good approximation if we find good solutions. There are two types of solutions that one can find, and one are local minima. And now, in this language of functionals, local minima are solutions of this equation such that if you would look at the second derivative, now in field theory, this second derivative is really like a differential operator, like nabla, like box, and other terms. So it's an operator. Operator has, you can let it operate on a test function, and you can find eigenfunctions and eigenvalues. And a local minima is an operator where all the eigenvalues are positive or non-negative. Well, yeah, let's say non-negative eigenvalues. But then there is the other possibility where we find something which we call a saddle point. And the saddle point is that this operator, normally most of its eigenvalues are still positive, but has at least one negative eigenvalue. And so now in the usual language, these eigenvalues, this is just a curvature. If we only had one variable, the second derivative would just be the curvature. So if everything is positive, it means that we have positive curvature. If one is negative, it means that there is one direction in the field space where there is negative curvature. And that's then a saddle point. We are somehow on top of something. It's still a stationary point, but it's on top of something. It's unstable, negative eigenvalue. Okay, now we still have to remember that this our space time was special. We have to respect some boundary conditions. Namely what? Well, the solution. Okay, let me call the solution. Let us call the solution. If we find such a solution, I call it phi hat. And it lives in this Euclidean spacetime, so it's a function of tau, of our imaginary time, and then of the spatial coordinates x. And so it has to satisfy the same boundary conditions that we derived from the path integral. So this has to be periodic in the imaginary time. This is a bosonic field, so if we go to beta, it has to be the same as the value at 0. Second thing is we want the solution to be such that like far away we are still in the high temperature phase, and this is really a bubble. So only in the middle do we go to the low temperature phase. And so in terms of a phi field, the high temperature phase is where the value is 0. It's like here. So this means that we should also put the spatial boundary condition that if I go far away, then the solution should go to 0 to the high T phase. Okay, and we require the negative eigenvalue. This is then this saddle point. Okay, so now let me try to sketch what one could expect to find. So now the now solving is an equation of motion. It's normally a nonlinear equation of motion. I mean, if we had a harmonic oscillator, then the only solution we find is really like an oscillation. Then we know exactly what it is. But to find something like a local minimum, you really have to have some regions where you have positive curvature, some region negative curvature. It means that it's a nonlinear, has to be a nonlinear system. If one solves for equations of motion in a nonlinear system, usually there are many solutions. Like, okay, think about the Schrödinger equation. Even, I mean, with a given boundary conditions, usually one finds many different solutions, many ground state and excited states. This is even more complicated, so one can imagine to find many solutions. Usually we expect that the solutions we are interested in the solutions with minimal value of the action, because in the end it appears as e to minus se. So we want a small action because then the probability is finite, maybe something can happen. Solutions with minimal action tend to have maximal symmetries. A little bit like with a hydrogen atom, the ground state doesn't have any angular dependence, and then excited state have angular dependencies. So now I want to sketch what one could expect. And I sketch this, I can sketch it only in 2 dimensions, but it really means 4 dimensions. So I put this time coordinate here, and then the spatial coordinates here. And at first, I'm at 0 temperature. And 0 temperature means that beta is infinity. So then all dimensions are infinite. And in fact, in Euclidean space-time, there's no distinction between Euclidean time and spatial time. Both are just equal. And so if I want to draw like a profile of a solution with maximal symmetry, what do? Well, I draw a circle, or rather it's some solution. It's here, it's far away, it's 0, that's the boundary condition, and then in the middle it can have some profile. That's like my bubble, sort of my bubble. So it's it's a 4D symmetry. So it's 4D symmetry. 4D means that it's really symmetric in this time and all the 3 spatial and directions. And if we find such a solution, it's not guaranteed, but of course there are many interesting theories where do find such. Then this solution, what do we call it? We call it, this is the famous instanton. Sometimes instanton is meant in a more specific sense for a solution in a particular theory, but generically speaking, instanton is it is the solution of the Euclidean equations of motion with maximal symmetry. Okay, so now what happens when I take a temperature non-zero? So now temperature non-zero means beta is finite. And beta is finite means that this periodicity starts to play a role. So it's no longer time direction is no longer the same as the spatial direction. Somehow I get there somewhere then beta. But this beta, it's not really a fixed boundary, but it just means that whatever I draw here, I have to repeat it here, its periodicity. Now, on the other hand, the equations themselves, they have just the same, it's just the same differential operator, just the same equation. It likes to find the same type of solution. But now I have to deform the solution such that it has this symmetry. It cannot be any more spherically symmetric in the time because there's this periodicity. So somehow I have to take this solution and kind of reflect it here like this, but then I have to respect periodicity. And so one can maybe imagine that somehow the solution becomes a bit like this. It has to be periodic, but it remembers something about the old. This, I say that this has 3+1 D symmetry. So still it's probably maximally symmetric in the spatial directions, but now the time is different. These solutions are kind of difficult to understand analytically, and so they are not as famous as instantons. Doesn't mean that they would be less important, it's just that they are more difficult to analyze, but they also have a nice name. They are called calorons. Caloron because it's somehow like an instanton but hot, a bit hot. Okay, and then a third plot, which is actually maybe the most important for us, is now we take temperature very, very large. So what happens? Temperature becomes large, beta becomes smaller. But still the equations are the same. It's just the boundary conditions which are different. So somehow the equations, they want to put the field in some configuration, but it's squeezed. And you are simultaneously looking for a maximal symmetry. And so now maybe it's not too difficult to imagine that at some point you find a solution which actually is just constant has this symmetry in the space, but it's constant in time. It's kind of you squeeze this such that it's narrower than the typical radius of your solution. Then we say that this has 3D symmetry. And these solutions also have a nice name, which we already heard today. These are the sphalerons. Again, sphaleron is used, the word is used sometimes in a more specific sense for a solution of a particular system with certain fields, but generically, sphalerons are really solutions of these Euclidean equations of motion, which are constant in the imaginary time. So then they are really three-dimensional. So now this all sounds very, maybe it sounds, well, it certainly sounds very deep. Also, it maybe sounds difficult, but in some sense, it's not so difficult, at least in some systems. And the reason is that in the last case, let's remember that our Euclidean action is an integral of 0 to, maybe now I should have again inserted the h bar because it's so nice here in this context. It's an integral over the tau, then it's an integral over space, and then the Euclidean Lagrangian. And now, if I really have this solution which is independent of tau, then what happens is precisely the same that happened in dimensional reduction, that the tau integral is just trivial, and then we only have an integral over the spatial directions, and e to minus 1 over h bar s is e to minus beta 1 over temperature times the three-dimensional, something three-dimensional. And so this is like a, this is, one can say, this is now, what is this? This is minus 1 over temperature, and this guy here, it has the dimension of energy. In a thermal system, this is really the Euclidean path integral, so it gives us free energy. And what this describes, what this bubble, the solution describes, is the extra free energy that you need to make this transition, to generate this saddle point, and to make the transition happen, to go over the barrier, so to say. So we can say that's a delta F. So it's really, it should be like classical statistical physics. So actually, I want to now demonstrate that indeed this, we can understand this. In the simple context, this is really understandable and easy. But maybe time for a couple of questions.
Can you explain again what is this 3+1 symmetry, please?
3+1 means, okay, the one is just, I'm looking for maximal symmetry. There's nothing which says, I think I can always have three-dimensional 3D symmetry. For me, rotational symmetry in 3 dimensions. This means rotational symmetry in 4 dimensions. So rotational symmetry in 3 dimensions. I just put the 3+1 to underline the fact that there is also something happening in time, but it's not really a symmetry. It just means that the time coordinate here is separate. Here there is nothing happening in time, so that's why I call this just 3D symmetry. Time kind of doesn't play any role at all.
Okay,
so it's a little bit like just like a language to keep in mind that there are these 3 different cases, and this is kind of, this interpolates between a vacuum 4D and a thermal high temperature 3D symmetry.
Okay, thank you.
Do you have any intuition for this statement that solutions with minimal action have maximal symmetries?
I mean, I think the simplest intuition is just you think about the Schrödinger equation. You can find many solutions, and they are classified by the the different quantum numbers, and L is the angular quantum number. And if you have L non-zero, you have more energy. Ground state is always the one which has L0. So because and the reason is simply that in the Hamiltonian there is a term which depends on L, so it's just energetically it's favorable to set that angular momentum to be 0, because then it does not contribute to the energy. So basically any deformations that you have, they come with gradients, and gradients cost energy. And so you want to kind of have as few gradients as possible. That's the maximal symmetry.
And the negative eigenvalue didn't play a role yet, right?
It right. Well, it played a role in the sense that this solution. I mean, right. Yes, in some sense, yes. But then we'll come back to that. Maybe I should say. I mean, here I introduced different names for these solutions, but generally speaking, the solution which satisfies this condition is called. Well, has many names, maybe, but such. Is often called a bounce solution. And then the corresponding action is the bounce action. Okay, so now I want to sort of just demystify this a bit by showing that that we can, in the particular case where we really have only a scalar field and we are looking at this nucleation, we can really construct this bounce solution, bounce action, purely in terms of classical thermodynamics. Like, I don't know, 95% of things in advanced statistical physics, this goes back to Landau. I think everything that one finds about statistical physics is in Landau books. And so this is the Landau theory of nucleation also then. So the idea is the following. So we now go back to bubbles. We forget like these fields and everything for a moment, we go back to bubbles. But the bubble is really like this bounce. And so I have my bubble here. And let me say that this bubble now has a radius r. And so this is the high T phase. This is the low T phase. And the temperature is now below Tc. So I would like to go into this phase. So now the low T phase is so to say energetically favored. That's where we would like to go. Well, so it's better to say free energetically favored, maybe. And by that I mean that that we can look at I started by talking this delta F, and so actually exactly at Tc it's 0, but we can let's say that we Taylor expand it around Tc, and then we take del T dt delta F at Tc times T minus Tc, and then terms of higher order. So this is 0 because the minima are equal, but this is not 0. That's what I was trying to show with this slope. So this is minus delta S. Minus delta S is minus Tc delta S over Tc, and Tc delta S is delta energy. And delta energy is my latent heat. That's the latent heat. And so therefore, this thing is 0, and there's a minus here, so I write it as plus L, and I take the minus inside here, so it just turns these around, and divided by T, it gives me 1 minus T over Tc. So now we see that if temperature is less than Tc, then the free energy density, then this delta F is positive. That means that the high temperature phase has more free energy, and it's disfavored. We would like to go to the low temperature phase, which has less free energy, which is favored. Okay, so now we can write down this free energetic cost of forming such a bubble. What is it? So delta F is, if we go to this phase, we gain in free energy. We go to the low temperature phase, we gain in free energy. That means we have minus my delta small f, because we go to the low temperature. So this is negative. We have free energy smaller, and that's good. We want to minimize the free energy. That's the free energy density, and then I have to multiply it by the volume, because I gain a certain volume. The volume is just a sphere. But I also pay a price, because what I'm doing is I'm generating this wall, this boundary. And in statistical physics, boundaries, they always cost energy. They cost energy because there are gradients, there are derivatives. And if you evaluate the Hamiltonian, then gradients cost energy. And so if you have a phase boundary, then the energy per area, it's called the surface tension. Sigma, it's usually called. And so it's an area term. Surface tension is really energy per area, or free energy per area. Okay, so let me plot this. Let me plot the delta F as a function of R. So you, I mean, normally in statistical physics we think about large volumes, and at large volume this is a small correction because it's an area term. It's small corresponding to compared with the volume term, but at small r it's the opposite. R squared is more important than r cubed. So delta F starts by going up. If you generate a very small bubble, then the price you pay for the surface tension is larger than what you gain in energy. And then there is a maximum at large R. Then obviously this guy wins and goes down. And so what is our bounce? What is our saddle point? The saddle point is simply the point here. This is, I call this the critical radius. If I generate a bubble whose radius is smaller than the critical radius, then the bubble shrinks. Larger, it starts growing. And now you see the negative, like this is really, its curvature is negative. So this really corresponds, this R is kind of, now we are using classical notions, so it's not directly variable in the field space, but it really corresponds to the fact that if you consider fluctuations, then one of the fluctuating directions has a saddle point with a negative eigenvalue.
I never like this expression, pay a price, because I don't understand pay a price. It's like a condition to be a stable bubble.
It's not a stable bubble. It's that if you generate this bubble, then what I mean by paying a price is that you need free energy. Delta F is positive.
How much energy?
Yes, we'll compute that in a second. Yes.
Yeah. So if you find this RC, you find the maybe the volume of the bubble.
Well, basically this delta F, it's like here. We compute the delta F. It's positive. This means that the probability E to minus delta F over T is less than 1. If delta is very large, then the probability is extremely small. But it's a finite probability, and we want to compute this probability. That's what we are aiming at.
Yeah, understood.
Yeah.
Thank you.
Sorry, I think I got lost somewhere. Why did we change signs going from that expression to that one for the full?
This delta is for me, it's delta F is F high T minus F low T. But now I'm looking at things from the other side.
Oh.
My bubble is in the low T phase. So I'm in a domain where delta F is positive, high temperature phase is disfavored, it has more free energy. And so this means that low T phase has, well, it has smaller free energy. So this is positive, but by going to the low temperature phase, I'm then observing things from this side. And so that's what I gained. I gained this delta F, and that's why I put it as a minus sign. I'm normalizing thing now, I'm normalizing it to the low T phase. So this kind of typical statistical physics, that all the expressions that we write, they are really like one-liners, or not even like half a liner, but then somehow it's difficult to really keep in mind what they exactly mean and how to use them. And so let's also do this exercise, which is really a trivial exercise, but let's just do it because the result is interesting. So we look for now for the saddle point. So this means that we have to determine the value of R. So we say that delta, we just look for the 0. That's now the solution of the, I mean, if I were here, it's not the solution of the equation of motion, then I will fall down. Equation of motion, so solution is a stable, it's a point with the derivative is 0. So four pi r squared plus 8 pi sigma 8 pi r is 0. I can take this term on the left-hand side, and then I divide by 4 pi r. So I get that the RC is, if I divide by 4 pi r, then I have 2 times sigma L1 minus T over Tc. And then I substitute back. Maybe I'll take 4 pi in front. And then I always take let's take r squared times sigma as a common thing. So r squared has sigma squared, and that times sigma cubed, L squared 1 minus T over Tc squared. And then let's see if we manage to collect the terms. So in the first term we have minus 1 over 3 times then this r cubed. In the r there's a factor 2, so minus 8, 2 cubed is minus 8 over 3. And then in the second term, we have 4 pi, we have r squared, so there's a factor of 4 from there. And then sigma times sigma squared is sigma cubed, so plus 4. So 12 minus 8 is 4/3. So 16 pi sigma cubed 3 L squared 1 minus T over Tc squared. This kind of an expression. So what's the important thing about this expression? The important thing is that and at the end we want this. So the important thing is that if I send T to Tc, of delta F, well, it diverges pretty strongly. This action, the free energy cost becomes just infinity. comes infinity, one sees the critical radius becomes large. And if one goes towards DC, the energy gain goes to zero. We don't gain so much, but we always pay the price. So kind of energy gain goes away, and still we pay the price, and R goes, and so we really pay a heavy price. It goes to infinity. This means that e to minus delta f over t goes to zero, well, and extremely fast, exponentially fast as 1 over t minus tc squared. And that means that if we are at Tc, or just a little bit below Tc, then these nucleations just cannot happen. The cost of generating this single bubble, which would start to grow, is just too large. Of course, in an ideal world, if we could wait forever, then at some point this would happen. But in cosmology, we cannot wait forever, or we are expanding. We kind of everything happens in real time, and so in this time that is available to us, it's extremely unlikely that these fluctuations would happen. So this means that nucleations only happen after some supercooling. Okay. So now, maybe I should say that then sort of in real research work, when people are looking at these dynamics, then one really has to do all these things. One computes the nucleation, the bounce action, one estimates the wall velocity, and one tries to put everything together. And so, in sort of models in models, it is often let's say, I wouldn't say simpler, but it's not more complicated to solve like the field equations. Than to compute separately the quantities that we need in this classical Landau theory, than to compute sigma and L. Well, in particular, the sigma. Sigma is kind of the difficult thing to do. So therefore, very often then people, rather than using the simple formula, they really take these equations and try to solve them numerically, which in itself is an interesting and non-trivial problem, particularly if you have many fields. And we know that in physics, we understand we have to have more fields than just the physical Higgs field. So it's some kind of looking for a saddle point in a multi-dimensional field space. Well, it's a topic of its own, but I wanted to mention that as well. Okay, so now what we have done is we have tried to see something about the nucleation. Then the next step was this bubble growth, this the wall velocity. That's a very hard problem as well. And I will not discuss that. I would not be surprised if next week Thomas Constantin would say something about that. But it's also a problem which is not easy to discuss because basically it's not really solved, so to say. We don't have a very good understanding of how to do this computation well. In fact, there are lots of papers are being written still these days doing this, of course, in some models, but even in a simple model, people don't exactly agree on how to compute this velocity precisely. Maybe sometimes it's enough to just take it as a parameter for baryogenesis, and then you just take it out of the hat, but at the end of the day, that's maybe not so satisfactory. Anyway, so just to say that this is complicated physics, there are many open issues, and that's why it's also interesting. What I want to now briefly say at the end today is that, somehow it's, of course, sort of theoretically speaking, it's a little bit unsatisfying if one has to kind of know somehow all these ingredients, look at them separately, put them together, and then hope that everything is consistent. And so one can ask, is there some framework where all of this would come out, like in principle all at once? And now if there were such a framework, then this framework, what could it be? Well, I mean, we cannot solve like the full standard model, everything all at once. But what we can do is something, what we could hope to do is something similar from what we did yesterday. Namely, this is all very infrared physics, really long wavelengths, like up to the Hubble, it's really infrared physics. So we could try to find some effective theory which captures this physics. Notably, an effective description. And I mean, we saw this effective description yesterday, this dimensionally reduced theory, but there the problem was that the way we did it, it was really like only for static quantities. There was no real time left over after the day. But here, really, all this is very much in real time. The nucleations happen at some point, then the bubbles start to grow, and everything is really dynamic. And so I want to, I cannot justify this very well. Because often effective descriptions themselves, you cannot really, often it's kind of, these are things which are sort of almost obvious at the same time and extremely difficult to prove, because if you were able to prove it, then you would have solved basically the original theory as well. So what one is then basically one takes some fields, one postulates the most general description, and then there are some parameters, and then we match for the parameters, and then we think that this is working. So now for this kind of a problem where we have a statistical system evolving in real time, there is also an effective description, a notion which actually can do this. But somehow then it's sort of, this physics is maybe evolved enough that often one doesn't, I think most of, at least in our university, the students wouldn't learn this somehow automatically. So what is this description? So the description is, again, it goes, in some sense it goes back to Landau, but also more generally it is related to fluctuation dissipation dynamics. What is fluctuation dissipation dynamics? Fluctuation dissipation dynamics is the following. Suppose we are looking at things in real time. And now I'm looking at my field, for instance, this field phi. And I start from some state. I say that by hand I put the phi field into some configuration. Maybe it's a configuration which is close to my bounds or any configuration, some configuration here. But if I pull it out of the hat, then it's not necessarily a typical configuration. It's some configuration. So what happens in statistical physics is that if you take any configuration, then it evolves towards equilibrium. Well, why? Because by definition, equilibrium is the most likely configuration, or the set of most likely configurations. And if the system is what we call ergodic, so it basically explores all the phase space, and then on the average it goes towards the most likely one, just because there are most of those states. So the system is somehow evolving somewhere, until it hits it finds this space in the phase space. It finds these typical configurations. But it doesn't stop there. It continues to be kicked by the other particles in the medium. And there is some, it's like a Brownian motion. Well, actually, this Brownian motion is an example of this. So that's, and it goes on forever. It's always fluctuating. And so that's fluctuation dissipation dynamics. This part here is called dissipation because the field originally is somewhere in the wrong place. It has, so to say, too much energy maybe, but in particular there is some information in the field that shouldn't be there. That doesn't, there's kind of too little entropy, too much information. You want to dissipate away that energy and that information. And then once you are in the most likely ensemble, you have lost all information, but then there are still these fluctuations going on. So what is a nucleation? I mean, the same dynamics also would apply to the nucleation. There, if we start from a high, let's say high T phase, then maybe this is the high T phase. This would be the 0. We start from here after some supercooling, and then most of the time we are still fluctuating around the false vacuum, but so extremely rarely with this probability, we can also have like a large fluctuation. And if it's large enough, it's very rare, but if it's large enough, then this fluctuation actually brings us to the correct minimum. We don't go anymore to this minimum. We start rather fluctuating here. So these are just words, but now let me write an equation. So how does it work for the scalar field? For the scalar field, this dynamics is implemented by an equation which is an equation familiar from Brownian motion indeed, but now for a field, and that's the Langevin equation. And the Langevin equation, it's really a simple equation. It is just a normal equation that we would write, d mu phi. Normally we would write d mu phi plus v, maybe v effective prime phi. Normally we would write this 0. This is the equation, this is the Klein-Gordon or equation of motion for a scalar field. And so now what we have to do when if it's in vacuum, this is 0, there is nothing else here. It's just a classical equation of motion. But if this field is interacting with these other particles, with this medium, and this is only like an effective theory for this one mode, and the other modes are integrated out, then what these other modes do is just these two phenomena. There is dissipation. This field can lose energy into the other degrees of freedom. There is some coefficient, like in an effective description always there is a coefficient. I call this upsilon. And then there are some derivatives. As always in an effective description, I start with the smallest derivatives. And now if I have a medium, I can build a first order derivative. Because the medium has a plasma has a rest frame. And so if I'm not in the plasma rest frame, I can say that the plasma has a 4 velocity. And I call this u mu, plasma 4 velocity. I can write this and take a derivative. If I'm in the plasma rest frame, then rest frame u is 1, 0. 1 is in the 0 component, time component, then this is just a time derivative. And so this is a friction. It's really like a friction. So this is the dissipation. This is the dissipation. If I have this field, and if it's somewhere where it shouldn't be, then it dissipates its energy, its information into the other degrees of freedom. But energy is conserved. So if you take energy from the phi and put it somewhere else, then the opposite process must also be allowed. The field can also gain information from the other ones. And that's why you should never put in just friction. We always, very often in cosmology, we just need this term, this dissipation, because we are somehow far from equilibrium and we are kind of looking at something that happens here. And then we only consider the friction. But really, if we wait long enough, then we get the other process, which are these fluctuations, the psi. So what is psi? Psi is some stochastic noise. It just takes energy from the plasma and gives it to the field. It doesn't depend on the field. It is not a function of the field. It's the function of the other fields that we have integrated out. And so then, very often, so this is the noise. The average is 0. On the average, nothing happens. You go up or down. Average is 0. But there is a 2-point correlation function with some autocorrelator, and if in a certain limit, again, like effective theory, in some sense, the other degrees of freedom are much faster. These are the slow variables. Usually in high energy physics, we talk about high energies and low energies, but statistical physics, the corresponding language is really in time scale, so fast processes and slow processes. And our effective theory is for the slow processes. The fast processes are happening so fast that the slow fields see them as effectively as white noise. And so this is the fluctuations, this noise, and that leads then to this rare fluctuations, and the dissipation, rare nucleations, fluctuations lead to nucleations, and dissipation is important, for instance, for the wall velocity. That's why the wall velocity is finite, because the field is there, but it has friction, it feels the medium, and that slows it down. And now what I want to conclude with is, it all feels a bit like something out of, maybe something out of nowhere, or related. Is it related at all to what we did? Actually, it's very much related to what we did, because one can do the following nice thing. I kind of, maybe I leave it as an exercise, but I just formulate the exercise. Now, suppose you take a linear system, so where this one is really like just a mass. Then the left-hand side is a linear differential operator. This is linear in phi. This becomes linear. I can go to the medium rest frame if I want. Then I have a linear equation with the right-hand side. I can solve this with a Green's function. This is like what we learn in electrodynamics when we have a source and the Maxwell equations, we solve it with the Green's function. Now, suppose I take a 2-point correlation function of this field. 2-point correlation functions, we do it all the time in cosmology. Okay, I can, maybe I should call it x1, x2, y1, y2, gr, x1 minus y1. And noise. and then I take the average. This means now the average over the noise. And now it's extremely nice to show that just the if I take the equal time limit, it's extremely nice to show that this is nothing else than omega, the autocorrelator, times 2 over upsilon, integral over, I can go to Fourier space. I get a Fourier transform, and then 1 over what? EK squared. EK squared. And now that should ring a bell, because what we saw previously was that that the Matsubara zero mode had a 2-point function, which was t over EK squared. Non-zero modes had Matsubara frequencies, here zero mode didn't, so it's exactly that. It's a Fourier transform of that, provided that this combination is 2 times omega over 2 times upsilon is t, and that is sort of the, well, that is also known as the fluctuation dissipation relation. That these fluctuations and the dissipation, they are actually not independent. They are related. They are related in a way that drives the system towards the correct equilibrium state. Okay, so I will stop here. There's lots of things came at the end, but I just wanted to say that in principle, one shouldn't be afraid of this complicated physics, because really it is part of a more general framework. And in principle, one could address all these things from one equation. In practice, it's very difficult to handle this equation. So in practice, we factorize things into various parts, but sort of conceptually, it is really doing non-equilibrium statistical physics in a system which has some rare but important fluctuations. And that's then one of the ingredients we need for baryogenesis. Okay, thanks.
Thank you, Mikko. Yes.
Professor, sorry, but I lost the meaning of this figure. Like this fluctuation, like generates a bubble?
This is not a bubble, sorry. This
No,
was just
at the end.
This meant that we normally, often in cosmology, we are looking at something with some field which is out of equilibrium, like, I don't know, inflaton, and then it moving somewhere. So often we are only looking at this part. Then we are looking at dissipation. Then we only need some friction, some rate, like a damping rate or so. That's my upsilon. But if we are trying to understand the full problem, then then in particular this problem with the nucleations, then it's not so much the dissipation which is important. It's that what we wait and the system is really in equilibrium. And then there are still these fluctuations. And so it's this, then every so often, but extremely randomly, there can be a large fluctuation, and that's then the nucleation. That takes us to a completely different minimum. But the important thing is that this physics, the physics of fluctuations and the dissipation, they are related. And these two coefficients are not independent, they are really related.
Okay, so this large fluctuation would be the nucleation that
Yes.
forms some bubble.
Yes, exactly.
Okay.
Yeah.
I have one question. But it seems it's important to know then, to have a theory of the fluctuations,
Yes.
to have some
Yes.
description of the
Yeah, exactly.
stochastics.
Yeah. I think that, and it's somehow this nucleation computation just sort, it has taken many decades for people to even formulate. I mean, so it's kind of very difficult physics. So even though at the end it's very simple physics, but it's difficult to put it together. So somehow, yeah.
Could you comment briefly about how usually people would calculate that surface tension in the bubbles that you're trying to model in this early universe stuff?
Surface tension is nice because the surface tension is really the energy per area of this wall. So if you had to compute it, you would simplify life by just going to TC, and then you don't have these bubbles. You have just a planar surface. So and then you take just a planar surface, and then you compute the extra energy that it costs. It's not, analytically speaking, it's not so much simpler than doing the full bubble. But then in some systems where people want to do like some numerical simulation or so, then it's a whole lot more simple to look at the planar surface than a round surface. Because normally, for instance, we put a system in a periodic box. And in a periodic box, it's easy to have, well, you cannot have one planar surface because you have to be periodic, but it's easy to have two planar surfaces. So you can measure 2 times the surface tension by having 2 planar surfaces. That's a fairly simple thing to formulate and even to measure in practice.
I think there's one question online by Juan. Why did we only consider the scenario of a saddle instead of other one with the local minimum? So,
I mean, the local minima are these are the stable phases or metastable phases. These are the things which are kind of simple to address. I mean, these are the things that we were trying to compute yesterday, like the free energy in that phase or in the other phase. So that was kind of work done. And so today the challenge was to then see how we go from one phase to the other phase. And so that's where you need the saddle point, the bounds. Yeah.
Any other question? No. If not, thanks again for the very nice lecture. And Rogerio, the colloquium will be here.
The colloquium is here. It should be a group photo after the colloquium.